review. This also probably means that if you ask one of the same questions that I went over in Tuesday's office hours or Wednesday's review session, I'll probably just say, hey, why don't you go watch the video sort of deal, and I probably won't do a complete thorough example of that here. So we'll start off with web work 27, number 1, and oops, let me pull this up here and get my numbers. 27, number 1. So this says use spherical coordinates to evaluate out the triple integral. And mine looks like the triple integral over some region E of x squared plus 1 dv. E is the region that lies between the spheres, x squared, so E is between x squared plus y squared plus z squared is equal to 25, and x squared plus y squared plus z squared is equal to 100. And so we'd like to go ahead and evaluate this. Okay, so it says use spherical integration. And maybe before we even get to the spherical bit, I think that for this, especially when you have like a constant like this, remember constants are really nice in triple integrals because constants are just going to be a volume. So one thing that I would consider doing for a problem like this is splitting this up and calculating out this bit. This is where all the complications lie here, and evaluating out this piece. So mine is just 1, but if you had some other number, right, like 3 or 5 or something like this, right, you could go ahead and essentially factor that out, right? You're allowed to pull out constants from the integrals. And so you could go ahead and do that. Now this bit right here, we know that this is a part of a sphere, right? So we have it's the part of the sphere that's kind of between these two pieces here. So we have a sphere of radius 10. So if I was to draw a little mini picture here, I don't know, maybe like right over here, we'd have a sphere of radius 10, right? Because 10 squared is 100. So here's maybe one sphere here, radius of 10, and a sphere of radius 5. Right? So if I was to go ahead, maybe I'll do green here to sketch this. So a smaller radius, smaller sphere, and again, this has a radius of 5. So whenever you do the triple integral of 1, remember that's just volume, right? So this is volume of kind of I think of this like a gumball, right? Because gumballs aren't solid. They have they're hollow in the middle. Sort of deal. So it's still, there's some gum, but it's not, solid all the way through. So if I was to calculate this out, maybe the fast way, I would do 4/3 pi r cubed, right? And so the radius of the outer sphere here is 10. So 10 cubed. So that would be as if it were completely solid. And then you have to take away the piece that's missing in the middle. And of course, the piece that's missing in the middle is another sphere. So 4/3 pi and 5 cubed. And so this bit right here becomes very, very fast. You get 4/3 pi. You can factor from both of those. 10 cubed is going to be 1,000. 5 cubed is going to be what, 125, I believe. So this ends up just being 4/3 pi and what, 875. And now you don't really have to worry about that, right? So we'll go ahead and add it at the end sort of deal. But that's just fine as is.
Wait, where did this come from? I'm sorry.
It's just the triple integral of 1, right? So this is the volume, okay. Right? So this is just this piece right here. So if you do the triple integral of 1, remember that's supposed to be volume, just like the double integral of 1 is area, or the single integral of 1 is arc length. So the triple integral of 1 is volume here. And so we just did the volume. And of course, right, we do the volume of the outer sphere, subtract away the volume of the inner sphere since it's hollow. And so the piece that you end up spending a lot of time on is this triple integral of x squared. And so we need to go ahead and maybe switch the function into spherical first. So instead of x, we can write what it goes rho cosine theta sine phi, that's x. I need to square that. And then whenever we switch into spherical, remember we need the rho squared sine phi. That's just the Jacobian as we switch from Cartesian into spherical. And then d rho, d phi, d theta. Once we've specified what order of integration we're going to do, rho first, then phi, and then theta, right, we can also set up our bounds. So if we go ahead and go back up here to the bounds, so this is specified, right, what region are we integrating over? We can see that this is going to be what rho is equal to 5. We already said this is a sphere of radius 5, so rho equals 5. And this is going to be rho is equal to 10. Of course, if you want to take this a little bit slower, right, on our formula sheet, we have a transformation equation that goes from Cartesian into spherical, and it says that x squared plus y squared plus z squared is equal to rho squared. So you could do an intermittent step here, right? To do rho squared is equal to 100, take the square root on both sides, and either way, you should be getting to rho is equal to 10. So the way that you enter into this region of integration is going to be from at rho equals 5, and the way that you exit is at rho equals 10. These were all of the equations that we had to kind of restrict our region by any means, and you notice that they happen to both be rho situations. So notice that theta and phi are not restricted at all. So the natural bounds for theta would be 0 to 2 pi, unless there's any restrictions. And the natural restrictions for phi would be 0 to pi. And so at this point, notice that all of these bounds are constants, right? 5 and 10 are constants. 0 and pi are constants. 0 and 2 pi, those are also constants, right? So everything's constant. And we have, if I maybe take one line here just to rewrite this, 0 to 2 pi, 0 to pi, 5 to 10. Notice we're going to have a total of 4 rows in total. So we're going to have rho to the 4th times, and if we collect all of our phi stuff, we're going to have sine cubed of phi. And if you collect all of your theta stuff, you're going to have cosine squared of theta. And then d rho, d phi, d theta. So notice we have a function of rho times a function of phi times a function of theta. And this is exactly what we need if we want to split this up, right? So you're allowed to make this 0 to 2 pi of cosine squared theta d theta, and we could evaluate this, times 0 to pi of sine cubed phi d phi, and then the integral from 5 to 10 of rho to the 4th d rho. And so we could evaluate these each individually. And so, for instance, the rho one right here would be rho to the 5th over 5, and then we would have to plug in 5 and 10. And last night at the review session, I mentioned that I would talk a little bit about, like, if I wanted to turn this into an exam question, right? Because these bits right here, you could argue, are kind of cumbersome in order to evaluate out these two integrals right here. But what if I told you, right, I gave you this exact problem from WebWork here on the exam, and I gave you the following two pieces of information. I told you, maybe hint, the integral from 0 to pi of sine cubed of u du is equal to 4/3, and the integral from 0 to 2 pi of cosine squared u du is equal to pi. So I give you these two integrals right here as a hint at the beginning of the problem, right? Now notice that these exact two right here have come up. We want the integral from 0 to pi of sine cubed, which according to this hint, this is going to be equal to 4/3. And of course, you did this in calculus 2. You need to use a U substitution for this, but we explored kind of completely what happens if you have kind of powers of sine and powers of cosine. How would you actually go about evaluating these? So this one, you end up converting, two of the sines or sine squared into 1 minus cosine squared. Then you do a U substitution, and there you go. This one, you need to use the power reduction rule. Again, this is the other one that I told you, that the integral from 0 to 2 pi of cosine squared u du, so in this case, the variable happens to be theta, that this equals pi. So with these two hints right here, this goes from something that sure takes a while and kind of has a bit of emphasis, in calculus 2, to something that ends up being very quick, right? Because now with that information, you can just plug those in. But again, you can, of course, pull these aside and use your Calc 2 knowledge, and you can, see that I'm not lying to you about these things. So 4 pi over 3. And then if we evaluate, this doesn't seem particularly fun, but 10 to the 5th minus 5 to the 5th divided by 5 plus 4/3 pi times 875. I have rather large radiuses here, but remember you have to include that bit there. And this right here, right, you don't need to simplify any more beyond this. WebWork would, accept this perfectly fine. Of course, if you had to turn it into like a D2L answer or whatnot, you could, of course, like factor out the 4/3 pi and evaluate out 10 to the 5th minus 5 to the 5th over 5, then add the 875, and then take that result and multiply it by the 4 pi over 3. So this would be a way to enter it into D2L if one was so inclined. All right. Any questions on this here?
Yeah, I had a real quick question.
Yeah.
So I understand how we calculated out the volume in between the two spheres, but
Okay.
what does the other, like the x squared integral, what does that area represent?
So this one wouldn't be an area or a volume necessarily. This one would be as if you were to take, right, this is the x-axis here. And remember, integrals are always adding something up. So because it's a triple integral, you're adding up something over a 3-dimensional region. So all inside of this 3-dimensional region, there are lots and lots of points. And of course, all of these points have an x value, a y value, and a z value. So it's as if you just take the x value from it, right? Because we're just doing x here. You just take the x value from the point and you square it, right? So therefore, since you take the x value and square it, right, anything squared is going to be positive, right? So you're adding up lots and lots of positive numbers all throughout this kind of hollow sphere here. And of course, if you had like a real world situation, like for instance, we had in last night's review session, we had a function where the, it gave out temperature, right? And you could calculate out like average temperature. So you can imagine like if you had a few heat sources, maybe you have a heat source here and you have a heat source on the other side here, right? Then, adding all this up, maybe it depends on the x value, right? How close it is to this heat source. And then adding all of this up and maybe dividing by the volume would give you like the average temperature inside of the sphere. You could also do stuff like, if this was, maybe you have bees in there, right? That's my other example, some particle-like thing, or maybe mosquitoes or something. And again, maybe you have those heat sources and maybe there are more mosquitoes or more bees drawn to, these points right here. And so they're more dense there. So if you imagine as x squared as some density function, then in this case, it would be maybe a bee density function or a mosquito density function. Then by doing the triple integral over this interesting cage, right? So this, you could think of this as an interesting cage that houses bees or mosquitoes or some, particle-like substance. Then adding all that up would tell you how many bees are in this cage or how many mosquitoes are in this cage. Does that sort of make sense?
Yeah, that makes sense. Thank you.
Cool. But because, right, we know at very least that this is positive, right? We know that our final answer here for that piece anyway ought to be positive. And you spend a little bit of time playing games and whatnot, you can also verify or kind of get some estimate as how positive should this be. But at very least, if you got out a negative answer, you should be alarmed because you were integrating something squared. And so when you add up a bunch of positives, you ought to be getting a positive number. All right, let me open up chat here and see, can you explain solving for phi? Well, in this case, there wasn't really any restrictions on phi, just like there wasn't really any restrictions on theta. And so it just goes from its natural bounds from 0 to pi. So in this case, we didn't have any, but certainly we had some, like last night in the review session where we had just the top half of a sphere, right? A hemisphere. And we talked about how to solve for phi either from an algebraic viewpoint or from a graphical viewpoint. So you can either look at the structure itself and say, when are you hitting the structure, right? When are you hitting this region that you ought to be integrating over? And then that could help you solve or at least visualize what would be reasonable bounds for phi. But then you can also use the equations themselves, right? There's always an algebraic viewpoint for these things. And so you could use the algebraic viewpoint in order to solve for what your restrictions on phi would be. Example from the textbook 3 on page 1069. So we did this one, or we talked through a fair amount of it on our office hours on Tuesday. So I think I did the majority of the exciting pieces. But also this one essentially just comes from the webwork problem that we did, right? There was another one in webwork that was sine, at least if it's the one that I'm thinking of, sine of x plus y divided by x minus y, I believe. And the textbook one here is this e to the x plus y divided by x minus y. And so it's very, very similar. A vote for webwork 25, number 3, that would be fine. But Kat, you also, the one who suggested the webwork 27, number 1. So I'll put that on the list here, but I want to make sure that everyone gets a chance to ask questions. So webwork 25, number 3 should be on the list here. But the whole inverse trig sub thing, yeah, I'm not sure. So, I mean, there's maybe also an inverse trig sub thing. I'm not sure if that would be something that we would want to ask on an exam, right? Certainly the emphasis in this class is not about trig sub. That's really more of a Calc 2 integration techniques thing. And so, yeah, I'm not sure that we maybe even want to do this problem. It seems unlikely. Let's see, how would you know if there are any restrictions on phi? Okay, I already talked about that. 2:14, so 5 minutes ago. I'm still lost with phi. Josh, I think you mentioned phi a couple times. Did I cover everything? Oh, I think he left. He's not here. Okay. Would a question specify to do the question with a triple integral or double integral? Not necessarily, right? Because triple integrals and double integrals could be used in order to find volumes. But when you have a double integral and you're finding a volume, it's always between one interesting surface and the XY plane. And so kind of you're restricted on what you could actually accomplish with just double integrals. With triple integrals, you can have two interesting surfaces, right? It doesn't have to be just one interesting surface in an XY plane. You can have two interesting surfaces, and you just make that typically the lower and upper bounds for your Z integral. Yeah. How about number 11 on the practice exam? Okay, that seems like a good one to do next. I don't think I've done that one, but I'll take a look at it. So number 11 on practice exam. Let me pull this up. I have my D2L already opened here. So let's see, go to the exams and the practice exam for exam 3. And let's see if I can't. Nope, it's making me click on this. And then I can hit preview. Oh, wait, why does it? Where's my buttons? Here we go. There we go. Start. So number 11 goes like this, at least my number 11. So you can yell at me if this is not the same one that you have. So it does the iterated integral. First bounds are -1 to 1. Second bounds are 0 to 1. E to the x squared plus y squared times sine of y dx dy. And it claims that this is equal to 0, and it's a true or false style question, right? So we're trying to figure out if this is true or not. So let's think about first our region of integration here. So with our region of integration, we have x's ranging from 0 to 1. So x equals 0 to x equals 1. And then our y's are ranging from -1 all the way up to 1. And all of these are nice constants. So it's just a rectangle. It's kind of, this is like a 15-2 style setup here. And so what we're trying to integrate over is this bit right here. X, Y. The answer to this ends up being true. And this is kind of a clever thing that you have to do with this. If you were to look at each one of the variables, so our x variable and our y variable, you'll see that there's a lot of symmetry going on here, right? So for instance, if you plugged in negative values for x versus if you plugged in positive values for x, it wouldn't really matter in this case because the x value is being squared. So in terms of x, this function right here is considered an even function, right? So the even functions say that if you plug in the negative values versus if you plugged in the positive values, they actually give you the same thing. This is back in our, our algebra days. On the other hand, if you were to do this in terms of y, right? Well, you can see that you have this extra bit, right? You have the sine of y, and the sine of y is classically an odd function, right? And then you have this bit here that's all evens. So I'd like to claim that if you were to plug in a negative y value into this, then you wouldn't exactly get f of y here, but you would actually be off by a negative sign, right? You get the negative out, and you can, kind of play this game a little bit here on your own if you'd like, right? So if I plug in specific values, so let's always keep x at 1 just for simplicity's sake for the time being. And you could plug in things like 0.5 in for y, right? And sine of 0.5. And then you could plug in things like maybe like negative 0.5 sine of negative 0.5, right? And if you plug both of these into your calculator, you'll see that they're just off by a negative sign, right? So if you plug in a negative, you get something that's quite close to when you plug in just the positive value, like positive 0.5, but it's off by a negative sign. So this is called an odd function. And so if you look at this, there's a lot of symmetry going on here in the y direction. So notice that if you plug in 0.5 right here, there's also a corresponding point where you're going to be plugging in negative 0.5. And likewise, if you plugged in, 0.7 up here, there's a place where you'd be plugging in negative 0.7. Or if you plugged in 0.2 here, right? And of course, the x values all change, and I don't particularly care about the x values. The big thing is that there's a lot of symmetry in this y direction, right? And so let's say that when you plug this in here, you plug in the 0.5, that the function outputs, I don't know, 0.701, right? And then down here, right, at this point, when you input a y value of negative 0.5, you get, of course, negative 0.701, or whatever it happens to be, right? And then remember, the double integral is that you're adding all of these things together. So you take this value and you add it to this value. And likewise, whatever these end up being, maybe this is like 0.341, and down here, maybe the function outputs negative 0.341, right? It always has to be the opposite because, again, it's an odd function, right? And when you add all of these things together, right, there's a lot of cancellation. Basically, the entire square up here is going to be canceling with the entire square down here. And so that's why all of those positive numbers cancel out with all of those negative numbers, and the result ends up being true. Now, really quick, before I open it up to questions about all the stuff that I've just mentioned, there is a Calc 1 theorem. I think it's back in like chapter 4, section 5 or something like this, that brings this up. It says that if you have the integral from negative a to a of f of x dx, of course, back in Calc 1, right, you only had one variable, that this is 0, right, if f of x is odd. That again, basically all those positive numbers and all those negative numbers cancel out with each other. And you can start and stop really at any a value there. And the picture that usually goes along with this, and then I promise I'll open it up to any questions, right? So if you have an odd function, it looks something like this, right? There's kind of some symmetry about the origin here. And so if you go from maybe negative a to a, and it doesn't really particularly matter, right, what a is, it could be negative 1 to 1, like in our situation, but it could also be negative 2 to 2, negative 3 to 3, whatever, right? When you find the area under the curve, aka the single integral here, for this region, remember, if it's above the x-axis, it gets counted positively, but if it's below the x-axis, it gets counted negatively. And so all of this positive area perfectly cancels out with all this negative area, right? Because again, it's net area really, and you end up getting 0. So this is essentially what we're using here. In this case, this was a true-false question from the book. So this is where this came from. So this is a nice property about odd functions here. So because there's a lot of symmetry in the y direction and y gives you an odd function, that's why this all works out. How do we know odd and even functions? This is back from your algebra days. So odd and even functions originally come from polynomials, right? So if you have a polynomial with all odd degrees, so something like x plus x cubed minus, 2x to the 5th or something like this. This is a polynomial with all odd degrees. This is going to end up being an odd function, and you can verify the property for odd functions that I mentioned. If you have a polynomial with all even degrees, so something like 5 plus x squared minus, whatever, 4 x to the 82nd power, right? All evens, then this is going to end up being an even function. And then there are also kind of some classic functions, of course, things like sine is odd because it has this rotation symmetry about the origin. Cosine is even because it has the reflection symmetry about the y-axis. So yeah, this is a lot of stuff from your algebra days here.
So basically in that problem, like the bounds could have been anything and it wouldn't have mattered.
Correct. Right. So in this case, if I could easily make different versions of this by making this 3 to 3, right? Or 4 to 4 or 5 to 5 or anything like this. And you could also swap these out so long as, you have any even, so long as you have any odd function in terms of y, this would be true. But notice, right, if you were to try to actually find the antiderivative of this, it'd be extremely difficult. You would not want to find the antiderivative of this. And that's why it's kind of a more conceptual question, right? Because, you can spend hours or days trying to find the antiderivative of these things. It'd be very difficult. Okay, a quick question about in the textbook here, chapter review for 15. Talks about problems 1 and 2. Question is, are these true? So question number 1. Yes, this would certainly be true because everything's continuous. So yes, that one's true, and it doesn't need to specify anything more to you. It's just, it is continuous. Sine is continuous. X squared is continuous. For the second one here, I guess I'd have to draw the region a little bit. Oh, no, but this one ends up being false anyway. Your final limits of integration always have to be constants. So the left-hand side of the equal sign makes sense, but the right-hand side doesn't make any sense. So 1 is true and 2 is false. So that's from the textbook, some true-false questions. All right. So I guess if there are no other things on the docket, I could bring up webwork 25, number 3, and at least say a few words about it. And see if there's a way maybe we can make it more reasonable for an exam-like setting. My webwork's a little bit slow, so triple integrals, and this is problem number 3. Oh, I see here. So in this question here, it asks you to integrate, and mine is 2z divided by x squared plus z squared dv. And when you spend a little bit of time with this, you see that maybe doing dx, dz, dy, just based on the region here, right? The region has x's going from 0 to z, and then our z's are going from y until 9. So you can see the x depends on z here, and then the z depends on y, and then the y is just constants, 3 until 9. So this would be a good ordering. And so, yeah, the question is about this first bit here. If you wanted to integrate this thing with respect to x, right? So integrating this with respect to x, and again, you're kind of pretending that all of these z's are constant for the time being. You need to be able to integrate something like this, 2z over x squared plus z squared with respect to x. And so the big thing that you need to remember here is that the integral of 1 over x squared plus 1 dx is equal to tangent inverse. So it's going to be a tangent inverse style thing, but then you have to do a little bit of guess and check sort of deal in order to see, right, in order to get that z there, how much do we need to be off by? I would say with this one, you would need probably a significant hint if they expected you to do this in any sort of time setting, right? If I wanted you to do this in 5 minutes or so, I'd have to tell you something on this tangent inverse business and how to manipulate this, because this is kind of definitely in the weeds for calculus 2. So this is probably where I'll leave my explanation for this one, unless if more people, have interest of me, saying more work about this. But for the time being, I'll just end that one there. Request to draw the region for practice exam number 5. So let me pull up the practice exam here again. And sure, so I think this one actually has some randomization built in here. So this says to compute, and mine goes like this. So this is practice exam number 5. And I have the double integral over some r of 60 minus 5x minus 3y dA, where r is the triangle in the first quadrant in the xy plane bounded by 3y plus 5x equals 60. So this is one that actually had something very similar to this in your web work for 15.1. So 15.1 web work. You can do this in terms of volumes, right? So volumes, and in fact, one of the things on our formula sheet is volumes for a pyramid. And so this thing will end up being a pyramid, and we could calculate it out because we know how to calculate out volumes of pyramids. And so that would be one way to go about this. But actually in 15.3, we also learned how to integrate over general regions. So you could also do this with a 15.3 style method where you just actually evaluate out the double integral. So really it's up to you kind of how you would want to proceed with a question like this. Probably the most straightforward way would be using the 15-3 method. But really, again, the question is kind of drawing this out, right? So if I want to draw this region right here, again, it said that we're in the first octant. So we know we can restrict our drawing down to just the positive x, positive y, positive z, x, y, z. And again, this is a plane. Anytime you want to draw a plane, right? So really, this is an f of xy equals 60 minus 5x minus 3y. Or another way to say that, right? This is outputting z values. We're embedding the outputs into the z-axis here. So z equals 60 minus 5x minus 3y. And now you really see, yes, this looks like a plane. And if you still can't see it, right, you can rearrange it a little bit and you'd write 5x plus 3y plus z is equal to 60. And now this looks like the equation from the plane that we gave you, back in our 12-5 days. And so anytime you want to draw a plane, you need 3 points, right? And it's very similar to drawing a line, right? When you want to draw a line, you need 2 points, right? You just do 2 points and then you connect them with a straight line and that's it. So similar for planes, but you need 3 points. So of course, my favorite 3 points anytime that I want to draw a plane have to be those along the intercepts, right? Where they intersect the x, y, and z axis. So if you want to get 3 points, 3 simple points, right? You could do, okay, let's do where it intersects the z axis. So I'm going to go ahead and plug in 0 for x and for y. And then when I do that, plug this in, right? I get 0 plus z is equal to 60. And so of course we get that z would have to be equal to 60. So if I go 0 in the x direction, 0 in the y direction, and 60 in the z direction, right? Basically we have a point way up here at height 60. That's 1 point down. Of course, any of the other intercepts are also good. So right, what if I did x equals 0 and z equals 0? So if I do that and I plug those in, right, I get 3y is equal to 60. So that's going to give me that y is equal to 20. So again, x and z are now 0. So I don't go out of the page at all. I don't go up at all. I just go 20 in the direction of y. And then finally, one more, right? What is x maybe when I have y 0 and z be 0? And so in that case, we would get what? 5x is equal to 60, so x would be equal to 12 altogether there. So x would be equal to 12. And so a plane that contains these 3 points, well, we could just go ahead and draw a plane here. Of course, just like lines or whatnot, planes continue on forever, but we only wanted the piece of the plane that lived in the first octant here, right? There's another part to this. It mentions something about the XY plane in a particular curve. So in mine, it mentions that R, the region R, is this region in the XY plane bounded by the line 3y plus 5x is equal to 60. Notice this happens to be exactly what we have when we take our equation and we set it equal to 0. Right? So if I take this and I set it equal to 0, I would get 0 is equal to 60 minus 5x minus 3y. And when you add your 5x to the other side and your 3y to the other side, you get exactly this. So that piece of information right there is just saying, right, it's describing this line where this plane intersects the z equals 0 or the xy plane. So this R, this region that we're supposed to be integrating over, is in the xy plane bounded by this line. So that's our region that we're integrating over. Basically, this is just specifying that we want the entire pyramid here. We don't want any piece of it. We want the entire pyramid. And so, again, you could, at this point, right, set up some double integrals and evaluate those. But because this is such a geometric structure, you could use the formula on the formula sheet. We know that the volume of a pyramid is given by 1/3 times the height times the area of the base. And so the height in this case, well, we see that the pyramid goes up to a height of 60. And the area of the base, well, we need to examine the base here. The base is this triangle. And so you could even, if you wanted to draw a two-dimensional picture of what the base looks like, you know, something like this. We see the triangle, and here we have the positive x-axis, the positive y-axis. In the positive x-axis, it's supposed to go out to 12, and in the positive y-axis, it's supposed to go out to 20. So again, I'm just taking that same picture that I had there, just down on the table, and I'm flipping it up kind of how we normally see things in the xy plane. So still it goes out to 12 in the x direction and out to 20 in the y direction, but that's how that appears when I kind of flip it up and look at it straight on. And so the area of this triangle is going to be 1/2 the base of the triangle, 12, times the height of the triangle, 20. And so let's see, 20 times 6 times 20. So I don't know, 400 times 6, 2,400. 2,400. Are tetrahedrals and pyramids the same? Yeah. I can't think of any counterexample. Yes, yes, they are the same. Okay, there we go. I saw there was another question to draw the region of number 2 on the practice exam. So, okay, practice exam number 2. Oh, and actually, so this one we did in the my office hours on Tuesday, and we did a good picture and all that sort of stuff. So I'll just point you to that video there. Like I said, I'm not going to double up on these things. So please, so this was office hours on Tuesday. And we spend a lot of time with the picture on this one here. And the link to that is both on D2L, where you have the links for all of the videos for your classes and whatnot. It's just at the very bottom under the recitation stuff for today. And then it's also on Piazza. So either one of those. I watched it and it says below for the sphere, and we did the region above. So it says it's bounded below by the lower half of the sphere. So how is it bounded? Well, the region is bounded below by the sphere and above by the cone. So the cone should be on top and the sphere should be on bottom. Yes. Yep. So those are the surfaces, how it's bounding the three-dimensional region. Exactly. Good. So I think we've cleared up chat completely. More questions? Could you explain the true false on the last quiz with the 2 graphs? I don't remember a true false on the last quiz with the 2 graphs. Number 8 on the practice exam. If you can explain a little bit more about the graphs, I'll come back to this, Harrison. So number 8 on the practice exam. So yeah, number 8 on the practice exam. Oops. Mine goes like this. Integral from 0 to 2, integral from 0 to the square root of 4 minus x squared times, and the function here is the square root of x squared plus y squared dy dx. And so this is the thing that we'd like to evaluate. This one happens to be a multiple choice. But of course, right, it could just plop this down and say, hey, evaluate this thing. Oh, All right. So yeah. So let me do this one. And actually, so that was another thing that we did for my office hours on Tuesday. That was the first question that we went over, was this one where it has these two half circles. So actually I'll be pushing off on the Tuesday office hours video. We talk a lot about this. So I recommend watching that. Okay, so how do we evaluate this, right? Because it plops down this double integral for us and it says, hey, what's the answer here? And so there's a couple of different ways that we could start off this, right? Since it's already specified in order and everything, you could think about trying to integrate with respect to y. And classically, integrating something like this with respect to y, think back to calculus 2, it was very, very difficult. It required a trigonometric substitution and all that sort of stuff, and the answer ends up being very, very nasty. And so I'd like to actually emphasize not to just integrate this straight up with respect to y. And so anytime you just say that you're going to do something clever, either by changing your variables or switching the order of integration, which, by the way, looking at this, I also don't know how to integrate it with respect to x. So maybe, swapping and just doing x's first probably wouldn't be super useful here. Maybe. But either way, you need to draw the region of integration. And so if I was to go ahead and draw this, right? So we have, first off, some y bounds. We have y equals 0 here, and we have y equals the square root of 4 minus x squared. And then I have x equals 0 to x equals 2. So let's go ahead and sketch these. So again, quite often, I like to work outside in whenever I'm drawing a region of integration. So starting off with x equals 0 and x equals 2, these are just telling me kind of my tick marks where I'm going to be, where my picture is going to live. So it's going to live between 0 and 2, because many times curves go on forever. It's just, we don't care about them, right? We're only interested in a particular region that we're integrating over. So now, of course, as I move inside, I've already taken care of all of the x stuff. Maybe my first and easiest line here, y equals 0. So y equals 0 is, of course, a nice horizontal line. Looks like this. And again, this would go on forever, right? Y equals 0 would go on forever, but I just don't care about it, right? Because my region of integration is focused between x equals 0 and x equals 2. So that's where we're going to be focusing. Now this one here, this upper bound of integration for y, this is certainly the most complicated one. Can anyone tell me what shape this equation corresponds to? What shape is this going to be? Hopefully you've done enough of these that it looks familiar. So yeah, this is going to end up being a circle, right? So this is going to be a circle. And the way that, right, if I just take this and pull it aside really quick, to see that it's a circle, right, we could square both sides. We would get y squared is equal to 4 minus x squared. And then I could add the x squared onto the other side. And now you really see, right, x squared plus y squared equals 4. This is a circle centered at the origin of radius 2. Because it's just the positive y values, right? Kind of if you imagine working backwards here to get to this, when you take the square root, you'd have to have the positive square root and the negative square root. But since we just have the positive square root here, it's only the top half of the circle. So the top half of the circle would look like this. But again, we're only drawing the curve between 0 and 2, right? So in reality, we just want to stop here, 0 to 2, and then we stop. So this right here is the region that we're integrating over. So exactly, this is going to be a quarter circle. And again, the radius here is 2. And now even, right, certainly the function itself is even screaming polar. But now when you see that your region is also a part of a circle, this is also screaming polar, right? Because you could have had, a situation here where maybe this wasn't screaming polar, right? It could be like x plus y or something like that. But still, when you see your region is a part of a circle, hopefully this is really pushing you towards polar integration. So let's go ahead and set up a polar integral here. I'm going to do it quick and then take questions. So if I do dr d theta, my r's are going to go from 0 to 2, and my thetas are going to go from 0 to pi over 2. And then I'm going to write the square root of x squared plus y squared. That's going to be the square root of r squared. So the square root of r squared is, of course, r, because, well, it's always positive, right? And I've messed something up. Can anyone tell me what have I messed up for my setup here?
Don't you need the extra r?
Exactly. Yep. So whenever you switch your coordinate system, right, you need to think about the Jacobian of the transformation. Of course, these ones are classic, right? When we switch into polar, when we switch into cylindrical, or when we switch into spherical, those ones should be just at your fingertips, right? And so, yeah, whenever you switch into polar, you need that extra integration factor, that multiplication by r. That's the Jacobian there. And so now the setup is done. The bulk of the work here is done. When I integrate with respect to theta here, I'm going to get pi over 2. And when I integrate with respect to r, I'm going to get r cubed over 3. Evaluate that from 0 to 2. That's just going to give me an 8 on top. So I'm going to get 4 pi over 3 as my final answer. And yes, that is a possibility, at least for my multiple choice. So a quick question for you guys. Maybe someone has a decent explanation that they wouldn't mind sharing for everyone. How was I able to just plop down a pi over 2 like this? Why could I do this? And how do I know that I can do this? And when can't I do this?
Sorry if anyone else was going to say something. It's because, at least I believe, that it's because there's no theta within the integrand. So there's nothing that this integral is going to depend on. So you pretty much, when you take the integral, you're just going to get, theta, because you have a constant of like 1 or whatever. No, yeah. And so you just plug in and since the bottom bound is 0, you just plug in the top bound, and that's just going to become the answer.
Yeah, so I skipped a step here, really, but we had right, an equation with just r's in it, an equation with just thetas in it. Well, in this case, the equation with just thetas in it, there are no thetas, so you can just use 1, right? And so you're allowed to break this up because you have multiplication of a function with just r's and a function with just thetas. In this case, there aren't even thetas. It's kind of like y equals 2 or something like this. There's allowed to be maybe x's in there, but it's, just very boring constant function there. And the other part of this that we need to emphasize is that we have a nice rectangle, right? The bounds do not depend on one another, right? So for instance, if I had here in the bounds here 2 sine theta, then this wouldn't have worked, right? Because that inner integration, that integration by r, would yield a theta, and then we'd have to integrate, we'd have to plug that in and then integrate there. But because everything was nice and constant, right, you're allowed to do this. And then just like you said, when you integrate 1, you just get theta, and then you plug in 0 and pi over 2, yeah, you get pi over 2. So this is something that, came up in 15.2, and I think especially as you're doing, especially in spherical, this sort of trick ends up saving a significant amount of time, right? If you can pull something off like this and you know when to do it and everything like this, then you're going to be able to get through some of these problems a lot faster. But it's, of course, anytime you're going to do a trick like this, you have to know when do they work and when do they not work. And so that's just why I wanted to kind of bring that up a little bit. All right, good. So I think that one's, I've said everything that I want to say about this. Any questions about this one?
Yeah, I think I just confused myself a little bit, but do we use the Jacobian when we're switching just the order of integration?
No, so for the Jacobian, you wouldn't need it so long as your variables are staying the same.
Okay.
So if you switch the order of integration, like y first, then x, and then you switch it from to x first, then y, then you haven't really changed your variables at all. And so you would keep you wouldn't need the Jacobian of anything.
Okay.
However, when you switch your variables, right, and instead of x's and y's, you now bring up r's and thetas, right? Then you need to know, then you need the Jacobian.
Yeah, for sure. Okay, thank you.
Yep. Should we be prepared for integrating a region that looks like a clover? So you can do this in polar, and it was brought up, I guess, even in Calc 2, we did some of these that look like clovers. And then we had at least one example, maybe two examples in our web work. I would say that for a lot of these that end up looking like clovers, the integration ends up being fairly difficult. And so it'd be one of those things kind of like up here, right? One of the first ones that we did, 27, number 1, where, right, if you don't have the hint that I gave you about these, then you end up spending a fairly significant amount of time. Maybe cosine squared is more reasonable here, right? Especially because the power reduction rules are on the formula sheet. But you would end up spending, quite often I've seen these ones where you end up with stuff like cosine to the 5th or things like this. Whenever you have clovers, kind of, you sometimes get more complicated things there. And so that would be my only concern, is how do you make it into something that's reasonably done in a time setting? That's my thoughts there. But yeah, so this is, right, this was homework 27, number 1 for anyone who joined late. And this one would normally take a decent amount of time, but with these two hints right here, if you say that the integral from 0 to pi of sine cubed u du is 4/3, and the integral from 0 to 2 pi of cosine squared u du is pi, then it becomes much faster. And this would be, you know, so maybe with a hint or something like that, you could make it feasible. Can you do an average value question? I guess I don't have one prepared, but I'm happy to do any of them that you would like. So if you have a particular web work question or whatnot, we also did, just as a heads up, on the review session last night, there was an average value question. It was the average value of a temperature function. So, right, it asks here to find the average temperature inside of this region. And so if you weren't there last night, and if you haven't watched this, I would recommend that take a look at that. I thought it was fairly decent. We had some good back and forth there. But I'm also, again, if you have a particular question that you would like to see on average value, I'm happy to do that as well.
Can I ask again about that quiz question? I'm sorry, I know I wasn't very specific last time. It was the true and false, where it was like the two like regions, and it was like one of them was like a whole circle, one of them was like a half circle.
Yeah, this one, right?
Yeah, this one.
Yeah. So have you watched or were you there at the office hours on Tuesday?
I'm trying to remember the days. I think I did watch this. I was just a little like confused about the symmetry part still.
Mm-hmm. Okay, yeah, I'd be happy to. I guess so. What about the symmetry? Can I help you with? I think you're muted, by the way.
Oh, sorry.
No.
Just like, how do you know, like, I think I was just a little like the first picture that you drew.
Mm-hmm.
How did you know, like, because it says like in the feedback or whatever, like you can see this by taking like f equals x. How do you know what to draw?
I guess the main thing is that I would be suspicious about made up properties, right? So we have a list full of properties that we know are true. And right, and if someone comes and they plot down a new property for you, I would already be on the side of, I don't know about this, right? And then you kind of just start trying some things and seeing, gain some intuition. So if you were to plug in something like very specific into this, so like a constant, well, then that ends up just being area, right? And for area, this ends up being true, right? So if you plugged in like 1 or something like that. However, for majority of non-constant functions, right, this would not be true. So, and you can just kind of play around. So I think down here, we have another picture as well. So kind of if you have a plane or something, right? So if you have this plane and you want to find the volume under this plane over this particular region, right? And if you were to just cut this in half, right? So I cut this in half and I say, I'm only going to find the volume of this half of it right here. And let's say that this volume of this piece right here ends up being, 10 or something. Can you then say that the volume under the entire thing ends up being 20? Right? That would assume that they both have the same volumes, right? But actually it's taller over here than it was over there. So there's not really a reason to suspect that the volumes would have to be the same in this case. And so again, you could plug in a specific, kind of if you do 10 minus x minus y or something like that as a particular function, this would show it to you. My favorite one to plug in is, kind of a relatively simple thing. For this one right here, I said, I made just kind of a conceptual argument about y, right? And so that's the way that I did it originally in Tuesday's office hours.
Okay, thank you. That helps a lot.
Super. Number 6 in the true false section of chapter 5 review in the book. Yeah, I'd be happy to do that. So number 6 talks about, so this is Stewart true false chapter 15 review. And it says that the double integral 1 to 4 and 0 to 1 of x squared plus square root of y times sine of x squared y squared dx dy is less than or equal to 9. It's less than or equal to 9. So yeah, we haven't really played around too much with inequalities for these things. Maybe back in 15.1 or 15.2, you maybe had like one property of something with inequalities. And basically it went like this. It goes, so here's our theorem, and let's assume that everything's integrable or continuous or whatnot, that if you have some function that's bigger than another function, then the volume under the bigger function, well, ought to be larger than the volume under the smaller function on any interval or any region that they're both well defined. So on any region D. So that's what the theorem said. And so that's the only kind of theorem that I can recall anyway that had this sort of inequality. And so I'm tempted to do something like that. Notice that in order to actually evaluate out this integral, this would be very, very difficult. I'm not even sure with, sine, there's nasty stuff inside, and then it's being multiplied by stuff there. That seems awfully horrible to actually find antiderivatives of. And so I'm going to try to find a bigger function that maybe is a little bit nicer, right? That we actually could integrate and we could find antiderivatives of and everything. And hopefully, if we do it decently well, maybe it'll yield 9, right? And if it yields 9, then we're just done, right? And we know that this has to be true. And so I guess, does anyone have a suggestion before I just blurt out the answer here? Again, I want something that's bigger than this function, my original function here, that's somehow not as horrible. Something that's bigger than it, but not as horrible. Anyone have a suggestion about what would be a good function to use? Okay, so quite often, back in our Calculus 1 days when we had stuff, I mean, we're a lot more interested in things like the squeeze theorem and stuff like that from Calculus 1. a common thing that we did is that we said for these trig functions, sines and cosines, we know at very most, sine is going to be equal to 1. So I'm going to go ahead, and if I want a bigger function, right, and sine's always less than or equal to 1, I'm going to go ahead and replace that part with 1. And now let's leave the other part the same. So again, here's kind of a nicer function that's larger than what we started with, right? Because its sine's not, exclusively equal to 1. It's usually less than 1, but every once in a while it comes up and it hits 1. Then it goes back down and it comes back up and all that sort of stuff. But so here's a function that's bigger, right, than the function that we started with, and is significantly nicer. So let's go ahead and look at our particular region. So in this case, we have from 1 to 4 and from 0 to 1 of our nicer thing now, and dx, dy. So if I integrate this with respect to x first, as it says I'm supposed to, I get x cubed over 3 plus x root y. And I'm supposed to evaluate this from 0 to 1, and then I have to do some y integrals. So that's me integrating with respect to x. Let's go ahead and plug in my endpoints here. So of course, if I plug in 0, I just get out 0. If I plug in 1, I get 1/3 plus root y. Don't need a bracket there. I'll use parentheses, I suppose. And then I'm going to integrate with respect to y. So if I integrate with respect to y, I get 1/3 y plus y to the 3/2 times 2/3. Double check. If I take the derivative of this, I should get back to where I started. So yes, this is a good antiderivative. And here I need to plug in from 1 to 4. So if I plug in that for my first bit, well, I'm going to get 4 minus 1. So that works out relatively nice. For my second bit here, I get 4 to the 3/2 minus 1 to the 3/2, right? So this is just going to be 1 here, and then 2/3 times 4 to the 3/2. So let's break this apart really quick. Let's go off to the side here. Of course, 1 to any power, we know that's going to be 1. So that's relatively nice. But 4 to the 3/2. So remember, whenever you have a complicated exponent like this, you're allowed to break it up, right? And so we can do, like, we have to raise it to the 1/2 power and we have to raise it to the 3rd power, but you can do this kind of in any order, right? And so I'm breaking up the 3/2 into a 1/2 and a 3 multiplied together there, right? So we do one and then the other. So if I do 4 to the 1/2 power, well, that's going to be, of course, the same thing as the square root of 4. So that's 2. And 2 to the 3rd power is going to be 8. I guess, I don't know. I probably don't need to spend nearly as much time explaining stuff like this because, I mean, we used to not have calculators in this class at all, right? And throughout the entire calculus sequence, it's kind of just, because of D2L and all that sort of stuff that we allow, kind of for some of these specific types of calculators. But now that you have the calculator, I mean, you would just take 4 to the 3/2, plug that into your calculator and be done with it, sort of deal. And you'd see it's 8 and be happy. But this is the way that, we used to have to spend more time and be careful with this. So 1 plus 2/3 times 7. So this is going to be, let's see, I'm going to do 3/3 plus 14/3. That's going to be equal to 17/3. So that's less than 18/3, which is, so that's less than 6. Right? So we got that this thing right here ends up being that if you were to integrate it and whatnot, that you get this, I already forgot, darn it, 17/3, right? So you got this 17/3. So this bigger thing gave out an answer of 17/3. So is this bit right here going to be less than 9? Well, yeah, and better yet, we know that it's going to be actually less than 6. So maybe it's 5, maybe it's 4, something like that. But yeah, it's going to be not only less than 9, but it's going to be less than 6 even. So the answer is true. And yeah, I miss paper exams too, Harrison. Good. More questions? How are you guys feeling about the exam tonight? I mean, nervous, right? Obviously. I was always nervous. 50-50. Oh yeah, thank you. I got this mug for, I think it was Christmas or my birthday one year. My wife's, so my mother-in-law, my mother is an art teacher. She's retired now or whatnot, but she always, pottery and stuff like this is, so she didn't make this, but she's like friends with the person who makes these. And so, yeah, it was nice. Yeah, feeling all right. Not sure what to do from now to the start time though. Yeah, I think that, it's, if you can relax at all, I would try to relax. And, if you're at the point where kind of you've done a fair amount, right? Ideally, on the day of the exam, you should try to relax as much as possible. It's kind of like, if you were running a marathon on a day or something like this, right? Because obviously your brain's a muscle, right? You don't want it to be fatigued, right? You probably wouldn't run a lot before you had to run a marathon on that day. I mean, obviously I hope that you're running a little bit each day before the marathon and training and getting prepped and all that sort of stuff. But on the actual day of the marathon, hope you had a good night's rest. I hope you had, some good meals. I hope that kind of your body's tuned and ready to go and all that sort of stuff. And it's the same thing for an exam, right? You don't want to be super fatigued going into the exam. And so if you just do nothing but math all day, yeah, it's tough. Any tips for transformations? I might just say I still have trouble with the U and V things. So, I mean, certainly I would review the transformation problems that came up on the quiz, right? So there was one where you had to change the bounds and it ended up asking, I believe, what quadrant the bounds would live in. And then you also had one, I think, with a true false, where it was not interested in the bounds at all. It was just interested in, as you transform kind of the function from, one set of variables, X's and Y's, to another set of variables. And those are relatively fast, right? It would be difficult to do a full transformation equation or full transformation problem on the exam. And so it's probably going to focus, I would guess, on just the bounds or just the function. So I would practice maybe doing those particular parts. Homework 27, problem 2. Let me take a look at this. Homework 27, problem number 2. Yeah, I'd be happy to talk about this. First octant. So, okay. Web work 27, number 2. So it says, express the triple integral below in spherical coordinates. And so mine is this triple integral over some region E. I have 7x e to the x squared plus y squared plus z squared dv. And it mentions that E is the portion of the ball So a ball is just like a solid sphere here. X squared plus y squared plus z squared is less than or equal to 1 in the first octant. In first octant. And so, yeah, the setup here maybe isn't super bad, but you do have to be careful, of course, with your evaluation for these things. So if you're in the first octant, notice that kind of the bounds for this, so the only information about E that's given to us, which of course needs to go in with the bounds of the integral up here, is that it needs to be less than or equal, right? This x squared plus y squared plus z squared needs to be less than or equal to 1. This is, of course, right, if we were looking at x squared plus y squared plus z squared is equal to 1, right? That's the boundary of this region. This, of course, is going to correspond to rho equals 1, right? So our only information that we're really given with this is that rho equals 1 is somehow the bounds of this. So you could probably guess, right, for your d rho, since it tells us to use spherical, that we're going to go from 0 to 1 in this case. Now, embedded in this first octant information, right, there's actually some other restrictions, right? So in fact, our thetas are going to go from 0 to pi over 2. Right? Because 0 to 2 pi would go all the way around, but we only want in the first octant, right? And of course, part of the first octant is the first quadrant. If you were to just restrict down to the x's and the y's, and the first quadrant lives here, right? Between 0 and 90 degrees, or 0 and pi over 2. And likewise, in the first octant, you want z to be greater than or equal to 0, right? And phi is your angle away from the positive z-axis, right? So you can include anything from phi equals 0 to phi equals pi over 2. But once you go beyond pi over 2, you actually have negative z values. So all that to say is that this first octant here is actually hiding some pretty important parts to this. So we have this right here as our setup. We can switch the equation, right? So we have 7, and then we're going to have x is going to be rho cosine theta sine phi. This e to the x squared plus y squared plus z squared is going to be rho squared. And then whenever you switch your coordinates, in this case from Cartesian into spherical, we need the Jacobian, or this integration factor. And we know that when we switch from Cartesian into spherical, it's rho squared sine phi. And so we can see that we have a fair amount of constants and some nice stuff and all that. But all of these are nice constant bounds here, and we have a lot of multiplication. And so if I wanted to actually evaluate this, well, let's see, we have the 7 that we can factor out here. Thetas are going from 0 to pi over 2, and our only theta stuff is that there's a cosine. Our fees go from 0 to pi over 2. And our phi stuff is that we have sine squared of phi. And then finally, for our rhos, we have rhos are going from 0 to 1. And we have rho squared times e to the rho squared. Oh, I'm missing one, right, from our x here. So this is going to be rho cubed. Now officially we're done with the Calc 3 part, right? This is the setup here. What we need to actually integrate and evaluate is the Calc 3 part. And the fact that we split it up like this, now we have 3 single integrals like this. And now we're officially back in Calc 1 and Calc 2 world, right? So of course, some of these are easier than others. So this one right here, when you integrate cosine, you get sine. And you can evaluate that fairly quickly, and that's just going to end up giving you 1. When you integrate something like sine squared, this takes a bit longer, right? We need to use this power reduction rule. And so the power reduction rule says, right, that sine squared is going to be equal to, what, 1 minus cosine of 2, whatever our variable is, I guess phi in this case, all divided by 2. And in fact, I like to usually distribute this. So let me rewrite this. So if you're dividing everything by 2, you have to divide the 1 by 2, and you also have to divide the cosine by 2. I'm going to write 1/2 here. So this is even, right, this is a rewrite that you do even before you evaluate out the integral. So now that we've done the rewrite, we can evaluate out the integral. So when you integrate 1/2, you get 1/2 phi. When you integrate cosine, you get sine. And don't forget about, right, that technically this is 2 phi. It's not just regular old phi. And so technically there's a small u substitution that's going on here. If you were to take the derivative of this, you don't actually get back to where you started. You actually need another 1/2, right? So this needs to be 1/4. And now you can double check. If you take the derivative of this, you get back to where you started. So that is indeed a correct antiderivative. And so from this, you can evaluate from 0 to pi over 2. 7, 1. And of course, I've saved the hardest one for last here. This one, you can start off with a u substitution, where u is equal to your inside function. du is going to be equal to 2 rho d rho. And so this ends up being the integral of e to the u. And let's see, if we go ahead and let's make this du divided by 2 rho d rho, equals d rho. So instead of d rho, I can put du divided by 2 rho, and we have rho cubed. So we can see that 1 down here is going to cancel with 1 up here, and you're going to get rho squared. And that's convenient because rho squared was supposed to be equal to u. So I can go ahead and swap this out and say that this is just going to be equal to u. And so don't forget, right, I have this extra 1/2. So maybe I could bring this out front here. And now I'm left with, I need to do the integral of u times e to the u. Can anyone tell me, how do I integrate u times e to the u? What method do I need to use? Yep, integration by parts. And so this takes a little bit, right? So you need to define some more variables and all that sort of stuff. I guess if there are no other questions and we don't have anything to do, I'll continue this. And we can get the result here, but I think I've taken this as far as maybe we ought to for this. But yeah, u e to the u is kind of a classic integration by parts one. So any other questions, or should we just continue this for fun? Doing the integration by parts. What's the du divided by rho? So this was, somehow I had to swap out. I wanted to swap out, instead of d rho here, integrating with respect to rho, I wanted to switch all of my variables to u's and integrate with respect to u. And so if this is my transformation equation, u equals rho squared, then if I take the derivative on both sides, I get that du is equal to 2 rho d rho. And so if I'm interested in how do I swap out my d rho, well, then you can go ahead and rearrange, dividing by 2 rho on both sides, and you get d rho is equal to du divided by 2 rho. And this is what it looks like in the integration. Du divided by 2 rho. What is E and what is rho? So there's only one E, and it's this bit right here. Yeah, no problem. All right, I think I'm going to stop the recording here.